Hello and welcome everybody to today's lecture about protection in electrical power systems. Our topic today is earth fault protection, and earth fault protection always is strictly related to the neutral point treatment, because the neutral point treatment governs the control and controls the earth fault protection. So let's start with the neutral point treatment and about a little bit statistics. As we can see, in high voltage schemes, high voltage systems, for example 110 kV, there is an enormous proportion of earth faults, shown in dark blue, versus short circuits. So in these grids, earth faults are the faults. In contrast to that, on the other side, in medium, rather low voltage, medium voltage system, for example cable systems, we have more short circuits than earth faults. And in the typical medium voltage range of 20 kV, we have both bad things from both sides. We have from the high voltage side the big proportion of earth faults, and from the low voltage side a high proportion of short circuits. So the 20 kV level and the medium voltage levels are very fault intensive. Now let's see, if something happens, most faults start during operation either from insulation breakdown or from other causes. So an insulation breakdown always happens at the maximum height of the sinusoidal waveform, and this leads to a single phase to ground failure. If such a fault evolves due to arc extension or for other causes, we may arrive at short circuits, which means we have fault current loops mainly through low ohmic conductors. In contrast, in earth faults, in most cases, we have non-metallic conductors that conduct this current. Now, the best way to understand the whole regime is starting with the isolated neutral. So we see on my right side the isolated neutral, which consists of a very simple transformer with a source impedance and a line, and also we need in this case the line to ground capacitances. So the fault starts, and by this, due to this low ohmic connection of one phase conductor to ground, which supposedly has 0 volts, we transfer the 0 volts onto the line. Now, these 0 volts also appear at the low voltage side of the transformer, and now we have a certain voltage loss across the transformer, which is given by the current flowing through this transformer. So, in isolated networks, usually this fault current is small, so there is no voltage drop across the transformer impedance, and the full voltage difference appears between the one side, which is grounded, to my right side, and the other side, which is the neutral, the system neutral. And by this means, the system neutral is raised in potential. It raises the potential, and to see what happens with the healthy phases, upon this raised potential of the neutral, we add the healthy phase neutral of, for example, phase number 2. And this usually results in a raised phase to ground voltage of the two healthy phases, which is L2 and L3. So in many modern medium voltage networks and high voltage networks, the neutral treatment is the so-called resonant grounded neutral. In the resonant grounded neutral, there is between the neutral of the transformer and ground a so-called arc suppression or Peterson coil inserted. Now, the fault starts. Again, the faulty line is in its potential drawn to 0. We have a full voltage across the transformer, so the neutral again is raised in its potential, and on this raised potential of the neutral, we add the healthy phase to neutral voltage of a healthy phase, and finally we arrive at the new phase to ground voltage, which is root 3 times as high as in the normal operation. A complete different treatment of the neutral is the solidly grounded neutral. So in this case, as you can see, the neutral of the transformer is solidly grounded, and if now a fault occurs, we have 0 volts at the end of the line, a high driving voltage, and we have a very high short circuit current. This short circuit current reduces considerably the voltage at the transformer low voltage neutral side, and in contrast, again the neutral of the transformer is raised, but only to smaller values, as we can see in the vector diagram. And on this raised voltage of the neutral, again we put and add the phase to neutral voltage of the healthy phase, and we arrive at the phase to ground voltage, which is far less below this factor of √3, which we have seen before. A mixture between these two opposing treatments of the neutral, either the isolated neutral or the solidly grounded neutral, is the low impedance grounded neutral. So here again the fault started with the lowering of the potential of the faulty phase, and this again carries a current from this transformer neutral through the resistor, and it's a circulating current which is in the order of some hundreds to maybe something like 1000 amps. That depends on the design of the system and its required protection. So this relatively small current has virtually no influence upon the voltage drop across transformer. So we have the full driving voltage between the low voltage side of the transformer neutral, and by means of this the transformer neutral potential is raised again. On this raised potential we add the healthy phase to neutral voltage, and we end up with a phase to ground voltage, as we can see in the phasor diagram, which is approximately the √3 fold of the undisturbed phase to ground voltage. So a short comprehension of these 4 types of transformer neutral point treatment. First we started with the insulated neutral, which is characterized by relatively low currents, and in this case the zero sequence current is decisive for protection behavior. Then we have the resonant grounded neutral, which is very similar. Again, the zero sequence current is used for protection purposes. Then the other class is the solidly grounded neutral. Here we have very high currents, and the faulty phase current is usually taken to locate the fault. And the in many countries used low impedance grounded neutral scheme results that we can use either zero sequence currents or faulty phase currents. How this is done in detail will be shown in the next presentations. I thank you very much.